Applications of FACTS controllers are explained as follows. Voltage control and regulation. FACTS controllers such as static bar compensators, SVCs, and static synchronous compensators, STATCOMs, are used to regulate voltage levels in power systems. They can maintain the desired voltage profiles, compensate for voltage fluctuations, and stabilize the grid during voltage sags or swells. Load flow control. FACTS devices can help control the flow of power on transmission lines by adjusting line impedance. This allows for efficient utilization of existing infrastructure and helps prevent overloads, reducing the need for costly line upgrades. Power oscillation damping. FACTS controllers, particularly thyristor-controlled series capacitors, TCSCs, and thyristor-controlled braking resistors, TCVRs, can dampen power oscillations caused by various factors such as generator imbalances or sudden load changes. This improves the stability and transient response of the power grid. Congestion management. By controlling the power flow on congested transmission lines, FACTS controllers can alleviate congestion in the grid. This helps in preventing bottlenecks, reducing power curtailments, and maintaining grid reliability. Contingency management. FACTS controllers enable rapid adjustments in power flow during contingencies, such as line outages or sudden load changes. This ensures that the system remains stable and continues to deliver power without disruptions. Reactive power compensation. FACTS controllers can provide reactive power support to the grid, improving power factor and reducing the overall demand for reactive power generation from power plants. This leads to better utilization of generating resources. Wind and solar integration. As renewable energy sources like wind and solar become more prevalent, FACTS controllers can aid in integrating these intermittent resources into the grid. They help manage the fluctuating power outputs and maintain grid stability. Long-distance power transmission. FACTS controllers can enhance the transmission capacity of long-distance power lines by regulating voltage levels and managing power flow. This is particularly important for transmitting power from remote generation sources to load centers. Harmonic mitigation. Some FACTS controllers can suppress harmonics and mitigate harmonic distortion in the grid. This improves power quality and reduces the risk of equipment damage due to harmonic resonance. There are several power quality issues that can affect electrical systems. Voltage fluctuations. Voltage sags, dips, brief reductions in voltage, often caused by starting large loads or faults in the power grid. Voltage surges, spikes, short duration increases in voltage, usually caused by lightning strikes or switching operations. Voltage imbalance. When voltages in a three-phase system are not equal, it can lead to uneven distribution of power among phases and cause overheating in motors and other equipment. Frequency variations. Deviations from the standard frequency, e.g., 50 or 60 Hz, can impact the operation of time-sensitive equipment like clocks and motors. Harmonics. Harmonics are non-sinusoidal waveforms that are integer multiples of the fundamental frequency. They result from nonlinear loads, e.g., electronic devices, and can cause overheating, equipment malfunction, and interference with communication systems. Voltage flicker. Rapid and repetitive changes in voltage can cause flickering lights and disrupt the performance of sensitive equipment. Voltage unbalance. Unequal voltages in a three-phase system can lead to uneven load sharing and reduced efficiency in motors. Power factor issues. A low power factor results from reactive power consumption in a system. It can lead to increased energy costs and reduced system capacity. Transient voltage. Short duration, high energy voltage spikes caused by lightning strikes or switching events can damage equipment and disrupt operations. Voltage swells. Short duration increases in voltage that exceed the normal range, often caused by sudden load reduction. Electromagnetic interference, EMI, and radio frequency interference, RFI. High-frequency electrical noise generated by various sources can interfere with the proper functioning of sensitive electronic devices. Interruptions. Complete loss of power for a short or extended period can disrupt operations and damage equipment, especially if proper backup systems are not in place. Voltage regulation.
Consistent and stable voltage levels are essential for the proper operation of electrical equipment. Poor voltage regulation can lead to underperformance or damage to equipment. Resonance. Resonance occurs when the natural frequency of a system matches the frequency of harmonic currents, leading to excessive. Proper design, maintenance, power conditioning equipment leads to its improvement. Common types of power quality mitigation equipment. Voltage regulators, stabilizers. These devices help maintain a steady voltage output by compensating for voltage fluctuations, ensuring that connected equipment receives a consistent voltage level. Uninterruptible power supplies, UPS systems provide backup power during outages, ensuring continuous power supply to critical equipment and preventing voltage disruptions. Surge protectors. Surge protectors, or surge suppressors, are used to limit the voltage spikes caused by lightning or sudden voltage changes, safeguarding sensitive equipment. Voltage sag and swell mitigation devices. These devices detect voltage sags, temporary drops, and swells, temporary increases, and provide compensating voltage adjustments to minimize the impact on connected equipment. Harmonic filters. Harmonic filters reduce unwanted harmonic distortion in the power supply caused by nonlinear loads like variable speed drives, thereby improving power quality and preventing interference with other equipment. Active power filters. These filters dynamically monitor the electrical network for harmonic distortion and actively inject counteracting currents to cancel out the harmonics, ensuring cleaner power supply. Power factor correction equipment. Power factor correction devices optimize the power factor of electrical systems, reducing reactive power demand and improving overall system efficiency. Isolation transformers. Isolation transformers provide electrical isolation between the input and output, protecting sensitive equipment from voltage spikes and ground loops. Dynamic voltage restorers, DVRs. DVRs automatically inject the necessary voltage to counteract voltage sags and maintain a stable voltage level during transient events. Active voltage conditioners, AVCs, similar to DVRs. AVCs correct voltage sags, swells, and interruptions to provide a continuous and stable output voltage. Static VAR compensators, SVCs. SVCs are used to regulate the reactive power in an electrical system, helping to maintain voltage stability and power factor. Energy storage systems. Batteries and other energy storage devices can be used to store excess energy during times of low demand and release it during peak demand, improving power quality by reducing voltage fluctuations. The selection of appropriate power quality mitigation equipment depends on the specific power quality issues present in a given electrical system. A distribution voltage regulator, DVR, is a device used in electrical power distribution systems to manage and regulate voltage levels within a distribution network. DVRs are typically installed on distribution lines and are responsible for maintaining a consistent voltage level as electricity is delivered from substations to residential, commercial, and industrial customers. Here's how they work. Voltage sensing. DVRs continuously monitor the voltage levels at specific points within the distribution network. Control logic. Based on the voltage measurements, the control system of the DVR determines whether voltage regulation is required. If the voltage is too high or too low, the DVR takes corrective action. Voltage adjustment. The DVR employs various techniques to adjust the voltage. These techniques might include tap-changing transformers, voltage boosters, and other voltage control mechanisms. Feedback loop. The DVR's control system operates in a closed-loop fashion, meaning it continually adjusts the voltage output based on the measurements it receives. This helps maintain a stable and optimal voltage level. Remote monitoring and control. Many modern DVRs are equipped with communication capabilities that allow operators to monitor their status and performance remotely. This is particularly useful for utilities to efficiently manage their distribution networks. Benefits of distribution voltage regulators include improved voltage quality. DVRs ensure that the voltage supplied to consumers remains within specified limits, preventing equipment damage and maintaining efficient operation of electrical devices. Energy savings. By maintaining voltage levels within an optimal range, DVRs can help reduce energy losses in the distribution system. Voltage stability. DVRs contribute to the stability of the overall electrical grid by regulating voltage fluctuations caused by varying loads and changing network conditions. Enhanced reliability. Voltage regulation contributes to the overall reliability of the electrical distribution system by preventing equipment failures due to voltage-related issues. Reduced voltage flicker. Voltage flicker, which can cause lighting fluctuations, is mitigated through the use of DVRs. Distribution voltage regulators play a crucial role in maintaining a well-functioning electrical distribution system, ensuring that end users receive reliable and high-quality power without voltage-related disruptions or damage.